Hello, I would like to welcome you to Lecture 16 of E-NG3N03. We'll start in this lecture to talk about MOSFET transistors, their biasing, and their characteristics. So this is a continuation of our discussion of transistors, and this will cover the rest of Chapter 8. Okay, we covered in the previous lecture the JFET transistor. We have seen that in the JFET transistor we have a reverse biased BN junction, and we can control the width of the conduction channel by varying the reverse bias on this BN junction. The MOSFET transistor, which really stands for metal oxide semiconductor field effect transistor, MOSFET, it applies a similar theory, but it does not really use a reverse PN junction. So for example, here let's take a look at this transistor here. This is a typical N-type E-MOSFET. So you have here two N-type electrodes. These are the drain and the source. And you have a B-type body or B-type substrate. This is an insulator. This is an SiO2 layer of an insulator. And this is a metal electrode. Okay. So here, when you don't apply any voltage between the gate and the source, there can be a conduction flowing here, because here you have a lot of electrons. Here you have a B-type material. There is no conduction channel here. There is no continuous region of N-type material where electrons can flow. So the way to get around that is simply to apply a positive voltage on this capacitor. This looks like a capacitor. There's an insulator here. So if I apply a positive voltage on the gate relative to the source, I'm actually attracting electrons to accumulate near the surface of this capacitor here. And this creates a channel. This creates a channel of high concentration of electrons, and these electrons can drift against the applied external electric field to cause current to flow. So current will be flowing in this direction, okay, from the positive electrode of the battery to the negative electrode of the battery, and the electrons are actually drifting in the opposite direction. Where do these electrons come from? They came because of the voltage applied to this capacitor. This really is a capacitor. There is an electrode, metal electrode here, and there is a channel, so the electrons get attracted to the positive the field that we have there, and this creates this conduction channel. Of course, the width of this conduction channel can be controlled by the gate to source voltage. It's like any other capacitor, okay? And by reducing the gate to source voltage, we can reduce this conduction channel and thus reducing the current that can flow from drain to the source. So this device effectively has 4 electrodes: the drain, the source, the gate, and then the substrate. So this substrate here, I will show you later. It's usually connected to the source. We usually don't take it into account, but in some other applications, they simply connect an electrode here, another electrode here, and then they can use it as a 4-terminal device. But for this course, we'll assume that this one is connected to the source. So this is really the basic symbol, the basic concept behind the MOSFET transistor. We have a capacitor. When you apply a positive voltage to that capacitor, it attracts electrons from the B substrate. All available electrons will get attracted. It will create an inversion channel or a conduction channel of electrons, and these electrons get swept away by the applied external electric field to cause current to flow. And you can control this current by changing the voltage applied to the gate. This is really a fundamental concept of the MOSFET transistor. And of course, for a MOSFET, you can have this called an N-type MOSFET because you have both the drain and the source are N-type materials, and current flow through an N-type layer, including this inversion layer of electrons that's created. We can have as well a B-type E-MOSFET. In a B-type MOSFET, you can have this will be P-type, this P-type, and you have here N-type, okay? And in that case, you have to apply negative voltage in the gate. Negative voltage in the gate will attract holes and then will allow current to flow from the 2 B-type materials. Now, this is also called an enhancement MOSFET. Enhancement MOSFET because when you have VGS equal to 0, when you don't apply any voltage, there will be no conduction happening because there is no inversion channel being created or no conduction channel being created. But in some other types of transistors, when there is a 0 voltage, there is actually some electrons existing. There is a layer that exists there because of the doping they create. So they can have some doping here in any type material, and in that case, it's normally it conducts current, unless you make the gate too negative relative to the source, and in that case you are repelling these electrons away from this region, and then you are eliminating the conduction channel. Okay, I spoken to you about the enhancement type MOSFET. Enhancement type MOSFET means when VGS is equal to 0, there is no channel here, and then the transistor is not conducting. D-MOSFET is different. D-MOSFET means when the voltage between the gate and the source is 0, you still have a conduction, an N-type material there. Maybe it's a very thin layer of N-type material. Okay, so there will be a flow of current when VGS is equal to 0. In order to remove these electrons and cut off this region, you have to apply a negative voltage between the gate and the source. This negative voltage will make this capacitor negatively charged, so the electric field created through this capacitor will repel these electrons, will push them away from the conduction region, and then will leave only here positive ions, and this will stop the conduction of the current. So the D-MOSFET is a naturally on transistor. When VGS is 0, there will be a current flowing from the drain to the source. But when you apply a negative voltage for between the gate and the source, as shown here, is a negative voltage, you are repelling these electrons, and the more the negative the voltage that you apply here, you are even reducing conduction through this channel more, and this is how you can control the value of the current flowing through this transistor. This is an N-type D-MOSFET called depletion type MOSFET, and the name comes from the fact that we are trying to deplete an existing N-type region. So this is an N-type material, we try to deplete it from electrons. So this thus the name depletion MOSFET, depletion metal oxide semiconductor field effect transistor. And again, for this D-MOSFET, you can have N-type MOSFET as this one, because conduction is happening through an N-type material. You can have B-type, so this can be P, this can be N, this can be B. And this again, a four-terminal device. A D-MOSFET can be used in the depletion mode when you have a negative voltage applied between the gate and the source, and in that case you are trying to repel the electrons away from this channel, or in the enhancement mode when you apply positive voltage between the gate and the source. This means you are even attracting more electrons, you are making this a channel more rich in electrons because of this polarity of on the capacitor. So this type of operation is called depletion mode operation. This type of operation is called the enhancement mode operation. Okay, we have of course, like in all other devices we have seen, there is a physical structure of the device and there is a circuit symbol of the device. In all these transistors, current will be flowing from the drain to the source, okay, and the current flowing from the drain to the source, we control it through the voltage applied between the gate and the source. Now, if this line here is broken, as shown here, I'll try to make it thicker for you. If this looks broken, this means it's an enhancement type transistor. Enhancement type means that naturally there is no current flowing here unless you make the gate to source voltage positive. In that case, you are attracting more electrons and so on. Now you can see this force arrow. It's not very heavily typed here, but there is an arrow flowing into this fourth terminal. This fourth terminal is a substrate. This is a fourth terminal I mentioned earlier, and here it's connected to the source. So this is a source, this is the drain, this is a gate, and this substrate is connected to the source. Okay, and the substrate here is a B-type. This is why the arrow is flowing in. So this is called an N-channel or N-type enhancement MOSFET. Now the other one shown here, again the line here is broken, and I will try to make it thicker for you to see. The line here is broken, and this arrow is flowing out. This is, if the arrow is flowing out, this is a B-type enhancement MOSFET. Usually you focus on N-type enhancement MOSFET. Now for the D-MOSFET, when the transistor is naturally in, so when you make naturally on, so when you make the gate to source voltage 0, there will still be current flowing from the drain to the source. You can see this is why they draw this line here as a solid line. It's not a broken line. It's just to show you that when VGS is 0, we can still have current flowing from the drain to the source. And now if this is an N-type MOSFET, then current will be flowing from the drain to the source. It's controlled by the voltage across the gate. This is an N-type material, this is an N-type material, while the substrate is a P-type material. The other type of D-MOSFET is a P-channel, which is not as commonly used as N-channel. This is a P-type material, this is a P-type material. This is a gate, it's of course connected to the electrode, and here we have the capacitor. This is the capacitor formed by the SiO2 layer of dioxide, so this will act as the capacitor. And you have here the substrate is an N-type material. So we will focus in this course on N-type E-MOSFETs and the N-type D-MOSFETs. So conduction is happening through N-type material and a layer or a channel of electrons. Okay, but remember these 4 symbols and the meaning of these 4 symbols. Now, a transistor and enhancement type MOSFET, really, if you try to draw one, maybe I could try to draw one for you here. This is how it looks like. This is enhancement type MOSFET. Okay. Okay, I'm sorry. We have to erase this one here. So this is the drain. This is the source. I draw here the gate. This is a gate. This is a drain. This is the source, and we have this substrate. Okay, it's a P-type, and it's shorted to the source. Okay. This and the current, as we agreed earlier, current will flow always from the drain to the source. Okay. Because the gate is connected to a capacitor, there is no current flowing into the gate. For this one, the current flowing here is always equal to 0. Ig is equal to 0. Okay. The current flowing from the drain to the source is controlled by 2 voltages: the drain to source voltage and the gate to source voltage. But in all the formulas given in the book of Floyd and in some other books, they focus only on the region, on the saturation region. So if you try to plot the complete characteristic of this transistor, you will see this is, if they say this is VDS and this is IDS, it looks something like this. There is a linear region followed by a saturation region, and in this saturation region, this whole thing is drawn for a certain value of VGS. So I can draw it for another value of VGS and then a third value of VGS, but it looks the same, a little bit shifted. So here it's either a linear function of VDS or it is not dependent on VDS. And in the book of Floyd, they assume that we really work in this, it's called saturation region. So the current is not dependent anymore on VDS. The current only changes when you are changing VGS. So here VGS1, another value of VGS, a third value of VGS, and so on. So this is one value, second value, a third value. So in that case, this is why they say the equation governing the drain current, the drain, or sometimes they call it ID, sometimes they call it IDS. It's exactly the same. It is the current flowing from the drain to the source. This current here is a quadratic function of the gate to source voltage, and they have here this is called threshold voltage. So if the VGS drops below the threshold voltage, you don't have a channel. There is no channel, no conduction channel, and in that case the current flowing is 0. But when the VGS exceeds the VGS threshold, then this creates a channel, and electrons are attracted to the surface of that capacitor. You have a channel and current can conduct. So I want you to understand very well that the current is really a function of VGS and VDS as well. But the formula given in Floyd assumes that we are in that region, which is really the region we use most of the time, that we already passed the linear region where IDS was a linear function of VDS, and now we are in the region where it depends only on VGS. You can see when you change VGS for VGS1, to VGS to VGS3, the current will change, and the change is quadratic. Okay, so keep this one in mind. And for historical reasons, they call this threshold, below which there is no current, the threshold voltage. And this is how we draw it in the VGS versus VDS domain. This is VGS, this is IDS or ID. So below, if the voltage for this N-type transistor drops below VGS, there is no channel and you get zero current. But once the voltage exceeds VGS, you have enough voltage applied to that capacitor to attract the electrons here and then create a conduction channel. So this line is not really broken anymore, and the current can flow from here to here, meaning that electrons are flowing in the opposite direction. Okay, let's consider the first example. The data sheet for an E-MOSFET gives ID equal to 500 milliampere when VGS is equal to 10 volts and VGS threshold is equal to 1 volt. So it will not conduct if VGS drops below this one. And this is an E-type MOSFET, so it's naturally off. Find the ID when VGS is equal to 5. The equation, and again here we are not taking VDS into account. The equation governing ID and VGS is a quadratic equation, but it has a constant of proportionality called K. We don't know what's K. If you read some of the advanced books, you'll see that K depends on the width of the capacitor, the length of the capacitor, the type of material the capacitor is built with. So the factor K has many other parameters underneath it. But here we need K, but this is why they gave us this value. They said when ID is equal to 500 milliamperes, we have VGS equal to 10. So from this piece of information, we can determine what is the value of K. We can determine what is the value of K. We go back to the equation, we have K. Once we know K, we can now plug VGS equal to 5 to get the new current value. So this is what I'm going to be doing here. This is the equation governing ID and VGS. Okay, I was given some value. I was told that when you put VGS equal to VGS1, you get a current I drain 1. So K is simply equal to I drain 1 over this quadratic factor here. This is 500 milliamperes. VGS1 is equal to 10 volts. The threshold voltage is 1 volts. So divide 500 milliamperes by 9 squared, so by 81, you get 6.17 milliampere per volt squared. These are the units of K. K has units of current per volt squared, because as you can see, it relates current to volt squared. Okay, and you can write it as milliampere per volt squared or as ampere per volt squared. You can write this one as 6.17 10 to the minus 3 if you want to. Now, I was given a second value of VGS and I was asked to determine what is the corresponding current. So I go back to that equation. I now know what is K. VGS is the same. VGS is a property of the transistor. So K as well as the property of the transistor did not change with biasing. So now I put the new value of VGS and then I can get the current. So this is what we do here. You put the new VGS equal to 5 volts. We already know this one, 6.17 milliampere per volt squared. I didn't write milliampere, but I know that the answer will be in milliampere. So you multiply 6.17 by 4 squared by 16, you get 98.7 milliampere. So this is how the current looks like for this transistor. Below 1 volts, if the VGS below 1 volts, there is no conduction. If VGS is equal to 5 volts, we get 98.7 milliampere. If VGS is equal to 10 volts, you get 500 milliampere. Okay, and of course, the higher the voltage, the higher the current until the transistor breaks down. You are making it heat and so on. So for safe operation, the current should not exceed a certain number, and this will be given in the datasheet. Now, for a D-type MOSFET, depletion type MOSFET, as we agreed, depletion type MOSFET is a naturally on. It has this characteristic curve. So when VGS is equal to 0, there is still current flowing, and this current is called IDS when the gate is shorted, IDSS. And in order to make the current go to 0, you have to apply a negative voltage between the gate and the source. This one here is for an N-type D-MOSFET. Okay, so this transistor is very similar to the JFET, and many books even will use the same expressions or the same quantities used to describe JFET to describe the D-type MOSFET. And for historical reasons, the equation governing the current here is equal to IDSS 1 minus VGS or VGS off squared. This is the same expression we used before for JFET. So when the voltage drops below VGS off, they don't call it VGS threshold here, then the current will go to zero. Okay? But when VGS exceeds VGS threshold, then you get a current flowing. And when there is no when VGS is equal to zero, so when this term is zero, so this whole thing will be 1, the current flowing is equal to IDSS. So this is called D-type MOSFET, and as I said, it is naturally on. It has already an N-type channel, but we can deplete this channel. We can deplete it by applying negative voltage up to a certain value, and then beyond that value there is no conduction channel, and then the conduction will terminate. Okay, let's consider an example here. For a certain D-MOSFET transistor, we have IDSS is given to 10 milliampere. This is a characteristic to the D-MOSFET. It's going to be given in the data sheet. VGS off is equal to minus 8 volts. So if the gate to source voltage drops below minus 8 volts, you get zero current. There is no channel anymore. Is this an N channel or B type N channel or B channel transistor? Is this an N channel or B channel? And find ID when VGS is equal to plus or minus 3 volts. Of course, because you have a negative threshold means that you are really trying to repel electrons. So this must be an N type or N channel D-MOSFET. Okay. Now to find the ID for different VGS, we have the quadratic expression, and again this quadratic expression assumes that we enter the saturation region, or what they call it, the bench off region. So in that case, the current is not dependent on VDS anymore. So we have the quadratic equation. We know what's IDSS. We have it. We have the off voltage. Then we are all set to put VGS equal to 3 volts or VGS equal to minus 3 volts. So, as I said, this is an N-type channel because of the off voltage polarity. Now, this is the expression that we have. We first put here VGS equal to minus 3 volts, then and VGS off is equal to minus 8. Then you get minus 3 over minus 8. 1 minus 3 over minus 3 over 8 squared multiplied by 10 milliampere. You get this number here. So this is a current when you applied a voltage of minus 3. And notice minus 3 did not give you a current of 0 because this device is naturally on. You have to go below minus 8 to make the current go to 0. Now, if you applied a voltage of 3 volts, now a positive voltage between the gate and the source, you put here this 3 volts, you put here minus 8, then you are actually making this whole term positive. Okay? And then you are getting a higher current, 18.9 milliampere. So if you try to draw it together, below minus 8 volts, there is no current. At minus 3 volts, we got the answer we got earlier. It's a smaller current. At 3 volts, we got higher current, which is 18.9 milliampere. So the current really increases by increasing VGS. Now we come back to the biasing of these transistors. There are so many biasing circuits. These are two types of biasing circuit. This one is called drain feedback. In that case, you connect the drain to the gate through a resistor. Remember, there is no current flowing through this resistor because the gate has a 0 current flowing in, but this makes the drain equal to the gate. The drain voltage equal to the gate voltage. Okay? And this, of course, you can use it to analyze the circuit. Another type of biasing is this one here. This is using a voltage divider. We have seen this one before, and because there is no current flowing here, this is indeed a perfect voltage divider. So we can control the VGS by changing the ratio between R1 and R2. So these are two possible solutions, and there are so many other E-MOSFET biasing circuits you can use. You can bias it through a current source and so on. But just remember, this is an N-type MOSFET because you can see the substrate has the arrow flowing in, which means that it is a B-type substrate. The current always flows from the drain to the source. It is the same current and is being controlled by VGS. Okay, let's consider this example. The data sheet for this E-MOSFET shows that ID equal to 10 milliampere when VGS is equal to VDS. Find the ID and find VDS. So for this transistor, we are told that data sheet will give a drain current of 10 milliampere when VGS is equal to VDS. And here I'm showing you not only the DC part, the black part is the DC part, I'm showing you the AC part as well. So you can use this transistor as an amplifier by connecting a capacitor here and then applying your weak signal between these two terminals here. So you can apply weak sinusoidal signal here, for example. And then this will cause fluctuations in VGS voltage, small fluctuations. These small fluctuations will be reflected in large fluctuations in the drain current, and then this will result in an amplified signal at the output port. So you get here way stronger signal. Okay, so here you apply weak signal, you get a stronger signal at the output, and this is how these devices work as an amplifier. But now we are worried about the biasing, and remember that the biasing will determine for us the transconductance, how the gain is going to be. If I apply a small change to VGS, how will that be reflected to change in IDS? So the biasing is very important, so we only focus on the DC part. Because we connected the drain to the gate and there is no current flowing here, then indeed VDS is equal to VGS. The drain and the gate have the same voltage. In that case, I know that I drain is equal to 10 milliampere. If I drain is equal to 10 milliampere, then I know that the drain voltage relative to ground, which is the source, is equal to 20 minus the drain current multiplied by RD. So I can simply take into account that ID is flowing this way, okay? And I simply say that the VD is equal to 20 minus ID multiplied by RD, which is equal to 1K. So by doing that, we can get VDS. So these lines summarize what I've said earlier. Because the gate is connected to the drain through a resistor RG, and the RG has no current flowing in it, then there is no voltage drop across it. This means that VGS is equal to VDS, and this means that the current is equal to 10 milliampere. This was a given. Now the drain to ground voltage is equal to VDD minus ID RD. VDD here is usually a term they use when they talk about transistors to indicate the source, to indicate the battery voltage. Sometimes we call it VCC, sometimes we call it VDD. It's the same. So as I mentioned earlier, the drain to ground voltage, and the ground here is the source, is VDD minus ID RD. This is 10 milliampere, this 1K. When you multiply them, you end up with 10 volts. So this is the drain to source voltage, is 10 volts, and it's equal also to the gate to source voltage. For D-MOSFET, again, there are several types of biasing. D-MOSFET, remember, this line here is not broken. Okay, this means that it requires a negative voltage between the gate and the source to make the current stops. Okay, but if you make it zero, there is a current flowing. There is a channel between the drain and the source. This is the depletion type MOSFET. Here there are a number of types of biasing. I'm showing here only one type, which is to connect the gate to ground through a resistor. This also self-biasing approach. You can bias it through many other techniques, and here I'm showing you can apply your signal here, and of course for amplification, and of course your output can be collected from here from the drain. So you get an amplified signal of the weak signal applied at the input. And there are so many other biasing circuits, but we'll just focus on like one or two of them. Okay. For this circuit, we would like to, we are given that the transistor has IDSS equal to 12 milliampere. We would like to find the drain to source voltage. Okay, and here again I'm showing you that the black part is the DC part. This is what we use to determine the operating point. But when we start to apply an AC signal, we are actually making all currents and voltages oscillate around the DC value. So we impose on the DC value a small value here, and this what creates a swing in the VGS voltage, tiny swing in the VGS voltage, and this amplified in a big swing in the drain current, which results in big swing in the output voltage. So you get an amplified version of your input signal here at the output. Now for this one, we know that the VGS is equal to 0, okay? We are given IDSS in this case, but here the tricky part is that IDSS is the drain current when VGS is equal to 0. So it must be the drain current in this case. Remember, the gate is connected to ground through a resistance RG, but there is no current flowing into the gate. Then the gate must be at 0 potential. This means that the VGS is equal to 0 because the source is also grounded. This means that the current flowing ID, which is flowing in the drain through the source, will be equal to 12 milliampere. So now we know what is the current. Now we can get VDS. It's one line. It's 15 minus IDSS multiplied by 620 ohms. So these lines summarize what I said earlier. No current flowing in the gate resistance RG, meaning that the gate is grounded, meaning that VGS is equal to 0. But by definition of IDSS, it's called the drain to source current when the gate is shorted. This means that I drain will be equal to IDSS. In that case, VDS is equal to VDD minus IDRD. This already we know what's ID is 12 milliampere, it's IDSS. This 620 ohm, this one is 15 volts. If you do all this, you get 7.56 volts. Now it should be clear to you why do you worry about biasing, because biasing will put you in the right point on the transfer curve. For example, if this is the transfer curve of a depletion type MOSFET, okay, if you are operated here, this will give you a certain slope to the relationship between any change in VGS and the corresponding change in VDS and IDS. Okay, so this means if you apply a small fluctuation here, this will reflect on a certain fluctuation here. So, and every point on this curve will have a different slope. So biasing means we're selecting the proper DC values so that we can determine the slope of the gain we're going to be getting, the value of the gain we're going to be getting. Okay, we'll talk more about that as we talk more about amplifiers and in examples.